Okay, hello everyone, in a new video in part 2 of chapter 11, which is the chapter of pressure and liquids in the third unit of mechanics. Then we have reached section number 3, which is given by pressure exerted by liquid. Previously, what we have done in part 1 is discussing the atmospheric pressure and stating Pascal's theorem, and we discuss also the pressure exerted by a liquid on a point in which this point is inside the liquid, but yet we didn't discuss how one can calculate the pressure or the atmospheric pressure, so which is the aim of this section. So let's consider a container filled with a certain liquid. So let's suppose that this is the liquid L of density rho L. Then rho L represents the density of this liquid, and let's consider a horizontal level inside this liquid in which the point A is located on this horizontal level. So the aim of this section is to calculate the pressure exerted by liquid on this point. So notice that here, if we consider the point B, so the point B is open to the atmosphere, therefore it will be subjected to the atmospheric pressure. Now if we are talking about the pressure at the point A, so pressure at A, so whenever we are interested in pressure or determining the pressure, we consider the point and we look upward. So above the point A there is a layer of liquid, then A in this case is submitted to the pressure of the liquid. And to the atmospheric pressure. Then the pressure at the point A can be written as PA is equal to the pressure due to the layer of this liquid plus the atmospheric pressure. Then what we will do in this section is to introduce how to determine the pressure exerted by liquid. So let's say here as a title, the pressure exerted by liquid at a depth h So let's suppose that this is the depth h. Why here the depth is important? Because as we have said previously, as the depth in a liquid increases, the pressure exerted by a liquid increases. So here the depth is important, so for sure the pressure must depend on the height or the depth h. Is given by, let me make it clear here that h represents the depth. This is h. So we can denote this pressure to be PL, or P for short. So this pressure is equal to the density of the liquid by definition multiplied by G multiplied by H. And we know that for any quantity in physics that is a combination or is introduced as a combination of quantities like multiplication and division, we can construct a triangle. So constructing the triangle of this formula, so here because we have multiply, then P, which represents the pressure, is at the top, rho L at the bottom, G and H. So for example, if you are interested in determining the density of the liquid, putting our hand over rho L, then rho L is given by P divided by G multiplied by H. So we are all familiar with this type of triangle that we have faced previously in this formula, which is like, it's very similar to the Archimedes upthrust, which is given by F upthrust is equal to the density of the liquid times the volume of the immersed part times G. Okay, so we all know how to deal with such type of triangles. Now it's left to introduce each quantity and its corresponding SI unit. So what does P represent? P is the pressure, but which pressure? Is the pressure exerted by a liquid, and its SI unit is given by PA, which stands for Pascal, or another SI unit for pressure is given by Newton per meter square. So the symbol is Newton / meter to the power 2 or meter square. So N / m to the power 2 stands for Newton per meter square. So as we can see here that the pressure has two SI units. So the main SI unit is given by Newton per meter square, but we denote this unit to be Pascal. So as we can see that the pressure depends, that the unit of pressure depends on Newton, and the Newton is the unit of the force. So later on we will see what's the relation between the pressure and the force. Now in rho L is the density of the liquid. And its SI unit is given by kilogram per meter cube. Whereas G is the gravitational field strength, which is related to the property of the planet in which we are performing the experiment. So we know that the unit of G is given by Newton / kilogram, which is Newton per kilogram in the SI. And finally H is the depth, at which the pressure due to a liquid is calculated. And we know that H represents a length, and the unit of length in the SI is meter. Now here let me give a quick example, just a direct application on this formula, which is given by the pressure at the point A only due to liquid, because we know that there are two pressures at the point A, the atmospheric pressure, because according to Pascal's theorem that liquid transmit a pressure, and the pressure due to the layer of this liquid. So we are interested in determining the pressure due to the layer of this liquid, which is given by the density of the liquid times G times H. So suppose that H is equal to 10 centimeters, which is equal to 0.1 meters in the SI, knowing that from centimeters to meter we divide by 100. Now, and suppose that G is equal to 10 newtons per kilogram, which means that we are performing this experiment on Earth. And the liquid here that we are considering is water. And the density of water, as we know, is given by 1000 kilogram per meter cube. So in this case, we know the density of the liquid, we know the value of G, and we know the height at which we are calculating the pressure. Then the pressure is given by 1000 multiplied by 10 multiplied by 0.1. Plugging this on the calculator, then the value of the pressure is given by 1000. Since everything is expressed in the SI, so the unit of P will be in the SI, which is in Newton per meter square, and this unit is usually denoted by Pascal. Now the next section is to introduce how one can calculate the atmospheric pressure. So the title of this section, which is section number 4, calculating the atmospheric pressure. So first here let me give the definition of the atmospheric pressure. So the definition, okay, previously we have discussed what is meant by atmospheric pressure, but here let me give the definition that allows us to calculate the atmospheric pressure, which is given by the atmospheric pressure is equal to the pressure exerted by a column of mercury of height capital H is equal to 76 centimeters. So in other words, the value of the atmospheric pressure is equal to the value of the pressure exerted by column of mercury. So here what does mercury represent? It represents a liquid of height H is equal to 76 centimeters. So the value of the atmospheric pressure is equal to the value of the pressure exerted by this liquid, which is mercury, of depth or height H is equal to 76 centimeter, and we know the pressure due to a liquid can be calculated using this formula. Pressure is equal to the density of the liquid times G times H. So now we know the value of H to be 0.76, or let's say 76 centimeter, which is equal to 0.76 meters. And the density of the liquid is equal to the density of mercury, which is given by 13,600 kilogram per meter cube. And the value of G in this case is given by 10 Newton per kilogram, because we are performing this experiment on Earth. So after we calculate the value of the pressure due to this liquid at this depth or at this height, so this pressure represents the atmospheric pressure. So let's convert H to the SI. So we have H is equal to 0.76 meters, because from centimeters to meters we simply divide by 100, and given that the density of mercury, so here rho stands for density, and this symbol Hg is the symbol of mercury. So we know that the symbol of carbon is given by capital C, symbol of hydrogen, for example, is given by capital H, symbol of oxygen is given by capital O, and similarly the symbol of mercury is given by Hg. Now, and okay, so the density of mercury is given by 13,600 kilogram per meter cube, and G is equal to 10 Newton per kilogram. And here let me say between the brackets that Hg, what does it represent? Represents the symbol of mercury, Now, using this given, one can calculate the atmospheric pressure, which is given by P atmosphere. Now here ATM stands for atmosphere. So P ATM represents the atmospheric pressure. So it's the density, it is equal to the density of the liquid. Here the density of the liquid is given by mercury, because as we have said from its definition, the atmospheric pressure is equal to the pressure exerted by a column of mercury. So the liquid here is given by mercury times the value of G, which is here 10 Newton per kilogram, and the depth at which we are calculating this pressure, which is this height, which is denoted by capital H. Now the value of rho Hg is given by 13,600, and the value of G is given by 10, and the value of this height or this depth is given by 0.76. Plugging this on the calculator, then the value of the atmospheric pressure is given by 103,360 Newton per meter square, and usually this unit is denoted by Pascal. So the atmospheric pressure is given by 103,360 Pascal. So usually we will follow this way in order to calculate the atmospheric pressure. So this is the way that allows us to calculate the atmospheric pressure, and let me here state the following note. Usually when solving exercises, data. So here I'm talking about how do we face this given in the problem. Usually the data of the atmospheric pressure in the exercises is given in the following way, as we shall see now, is given in the following way. Let's say in the following form, that P atmosphere is equal to 76 centimeter of mercury. So this statement here, the atmospheric pressure is equal to the pressure exerted by a column of mercury of height H is equal to 76 centimeter, is usually given in the following form, that the atmospheric pressure is equal to 76 centimeter of mercury. And here we must be very careful, because the first thing that we must notice is that this quantity which represents the pressure is not in agreement with the unit, because the unit represents the unit of height or depth or length, and we know that the unit of pressure is either Newton per meter square or Pascal. So notice that the quantity and the unit are not in agreement, but what is meant by the following is that, so this means, which means that the atmospheric pressure corresponds to the pressure exerted by a column of mercury of height. So why mercury? Because here they mentioned mercury of height H is equal to 76 centimeters. So because 76 centimeter, this value represents the value of a height because it carries the unit centimeter. So the depth or the height is given by 76 centimeters. So because now we know that the height is given by 76 centimeter, and we know that the liquid is is mercury, so we usually the density of mercury is given, and the value of G is given so usually is given by 10 newtons per kilogram, which means that we are performing this experiment on Earth. Then using this given, the atmospheric pressure is equal to 76 centimeter of mercury, one can directly determine the atmospheric pressure, as we shall see in this exercise. So exercise number 2, calculate the atmospheric pressure knowing that it corresponds to P atmosphere is equal to 76 centimeter, given that the value of G is equal to 10 Newton per kilogram and the density of mercury is equal to 13,600 kilogram per meter cube. So here, as I have said previously, that notice that this quantity is not in agreement with this unit. So we must rewrite this correctly. So 76 centimeter, this value correspond to the value of the height because it carries the following unit centimeter, and we know that centimeter is the unit of depth, height, or length. So we have that H atmosphere is equal to 76 centimeter. So previously we have denoted this to be H, but it's the same. Knowing that centimeter is not the SI unit of depth or height, in order to convert from centimeter to meter, we divide by 100. So then 76 divided by 100 is equal to 0.76 meters. So they are telling me that the atmospheric pressure corresponds to P atmosphere is equal to 76 centimeter. Here for sure they must have mentioned of mercury, so the liquid we are using is mercury. So if we determine the pressure exerted by 76 centimeter height of mercury, then we have determined the atmospheric pressure. Then the atmospheric pressure is equal to the pressure exerted by 76 centimeter height, column height of mercury. So the density we are using is mercury, so the density of mercury is denoted by rho Hg multiplied by the value of G, which is 10, multiplied by the atmospheric height, which is H atmosphere. Now the density of mercury is given by 13,600, the value of G is given by 10, and the atmospheric height is given by 0.76. Plugging this on the calculator, then the value of the atmospheric pressure is given by 103,360. Since all of these quantities are expressed in the SI, so the value of the atmospheric pressure will be expressed in the SI, which is in Newton per meter square. And knowing that Newton per meter square is usually denoted by Pascal. So the atmospheric pressure is given by 103,360 Pascal. And now let's move to the next section. So we have reached section number 6, and the title of this section is calculating the variation of pressure. Here the word variation means the difference. Okay. So first let me consider a container filled with a liquid. So suppose that this is a container filled with a liquid L. Of density rho L. And let's consider a horizontal level inside this liquid. And another horizontal level. And let's consider 2 points. This is the point A at the horizontal level 1, and this is the point B on the second horizontal level. So as we know that here, if you consider another point to be C, so C is open to the atmosphere, then C is submitted to the atmospheric pressure. Now as the depth in a liquid increases, the pressure exerted by the liquid increases. So A will be submitted to the pressure of this layer of liquid and to the atmospheric pressure. So as for the point B, so the pressure at the point B is greater than the pressure at the point A, and the pressure at the point A is greater than the pressure at the point C. So what about the point B? The point B is submitted to the pressure of this layer of liquid and to the atmospheric pressure. Now the aim of this section is to calculate the difference in the pressure between the points B and A. So we are interested in determining the difference of pressure. So PB, the pressure at the point B, minus the pressure at the point A, and this is denoted by delta P. Okay, so recall, what does delta represent? For example, if you have delta X, so it is X final, or X2 minus X1. If we have delta T is equal to T2 minus T1. And if we have delta L, so it's equal to L2 minus L1. So we are interested in determining the variation of pressure between the points B and A, knowing that the pressure at the point B is greater than that of the pressure at the point A. And let's denote the difference in height between the two horizontal levels to be h. Okay, so the variation of pressure inside a liquid between 2 points A and B is given by so delta P. So it's the difference between the pressure at the points B and the pressure at the point B minus the pressure at the point A. So here we have two choices. Either we say that PA minus PB, so this is delta P, or we can say PB minus PA. But always we start with the pressure at the point located at the lower horizontal level in order for this difference in pressure to be positive. So because B is located at a horizontal level lower than that of A, so we'll say that PB minus PA. So in this case, the variation of pressure is given by the pressure at the point B, which is located at the lower level, minus the pressure at the point A, which is located above A. So now if you know the value of PB, so in the previous section we have introduced the method how to calculate the pressure at the point B, and we have introduced the method that allows us also to calculate the pressure at the point A. So if you know the values of PB minus PA, this is a linear equation and one unknown. The unknown is delta P, so we can simply calculate delta P. But another method to calculate the variation delta P. So notice that the difference in the pressures between the point B and A is due to the layer of this liquid only. So which is given by the density of this liquid times G times H. And here let me make it clear that H represent the difference between the two levels. So previously, whenever we used to calculate the pressure at a given point, so H previously it represents the height or the depth from the free surface. But here in this case, H represent the difference between the two levels. So in brief, delta P can be calculated using two methods, either from this, or if we know the pressures at the point B and at the point A. So, and now let me say that what does each quantity represent and its SI unit. So because here we are supposing that PB and PA are expressed in the SI, so the value of the variation of pressure will be also expressed in the SI. So what does delta P represent? Delta P is the variation of pressure, and it's expressed in Pascal, or as we know, Newton per meter square. Now, what does PB represent? PB represent, or let's start by PA. PA is the pressure at the point A, and it's also expressed in Pascal, which is given by Newton per meter square. Now as for PB, PB represents the pressure at the point P. So it's also expressed in Pascal or in Newton per meter square. And rho L is the density of the liquid. And the SI unit of the density is given by kilogram per meter cube. And G is the gravitational field strength. And its SI unit is given by Newton per kilogram. And H is the difference of levels between points A and B. So because H represents depth or length, then it's expressed in meter, which is the SI unit of length. And now let's solve the following exercise, which is a direct application on all the previous sections. So this exercise is a bit long, but it's easy. So exercise number 3, each of documents 1, 2, 3, and 4, so they mention these documents, now we can use them, represents container filled with immiscible liquids. So here the word immiscible means that the liquids doesn't mix with each other. So the density of water is given by 1000, density of oil 800, and rho Hg is equal to 13,600. So recall that Hg represents the symbol of Mercury. So this density is the density of Mercury. So given that H1 is equal to 10 centimeters, so knowing that centimeter is not the SI unit of length, in order to convert from centimeters to meter, we simply divide by 100. Then 10 divided by 100. Then H1 is equal to 0.1 meters. Now as for H2, H2 is equal to 6 centimeters. Similarly, dividing 6 centimeters by 100, we got that H2 is equal to 0.06 meters. We have that H3 is equal to H1, so H3 is equal to H1, which is given by 0.1 meters. and H4 is equal to 4 centimeters. Then 4 divided by 100, so H4 is given by 0.04 meters, and H5 is equal to 3 centimeters. Dividing 3 by 100, then H5 is given by 0.03 meters. Now the atmospheric pressure is equal to 76 centimeters. So here let me add, there is something missing here of Mercury. So this is missing, but it's okay. And the G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. Number 1, they are telling us that A, C, E, and G, so this is the point A, C, E, G, are at the free surfaces of the corresponding liquids and submitted to the atmospheric pressure. So they are already telling me that these points are submitted to the atmospheric pressure simply because they are open to the atmosphere. Calculate the value of this pressure. So we need to calculate the atmospheric pressure. Notice that here in the given they are telling me that the atmospheric pressure is equal to 76 centimeter of mercury. So here also, before I start solving the exercise, notice that I didn't copy the following given, so let me copy it. Notice that the following quantity and the unit are not in agreement because the unit of pressure in the SI is Pascal or Newton per meter square, whereas centimeters doesn't represent the unit of pressure, it represents the unit of depth or height. So let's rewrite this given properly. Because this value carries the unit centimeter and it's related to the atmosphere, so in fact this value corresponds to the atmospheric height that allows us to calculate the atmospheric pressure. So 76 centimeters. From centimeters to meters we divide by 100. So the atmospheric height that allows us to calculate the atmospheric pressure is given by 0.76 meters. Now we need to calculate the atmospheric pressure, knowing that the atmospheric pressure in this case is equal to 76 centimeter of mercury. So the pressure due to liquid is given by the density of the liquid times G times H. So here the liquid we are using is mercury. So we replace the density of mercury. Now G is equal to 10 newtons per kilogram because we are performing this experiment on the surface of Earth. Since we are calculating the atmospheric pressure, then H must represent the atmospheric height. So P atmosphere is given by the density of mercury, which is rho Hg, multiplied by G multiplied by the atmospheric height. So the value of the density of mercury is given by 13,600 from the given here. And the value of G is given by 10. The value of the atmospheric height is given by 0.76. Plugging this on the calculator, then the value of the atmospheric pressure is given by 103,360. Since all of these rho, G, and H are expressed in the SI, so the value of P will be in the SI, which is a Newton per meter square. And another unit for a Newton per meter square is Pascal. So the atmospheric pressure in this case is given by 103,360 Pascal. Let me write here that atmospheric pressure is equal to 360 Pascal. And here also let me correct something, that this is A and not B. Now in number 2, the pressure PB is greater than the pressure of PA, justify. So this is the point B and this is the point A. They are telling me that the pressure at the point B is greater than the pressure at the point A, and this is reasonable because notice that B is located at a horizontal level lower than that of A, and we know that as the depth in a liquid increases, the pressure exerted by liquid increases. So in this case, the pressure at the point B is greater than the pressure at the point A. Now, number 3, calculate the pressure exerted by water at point B. So notice that here B is submitted to two pressures, to the pressure due to the layer of this water and to the atmospheric pressure, because we know that according to Pascal's theorem, liquids transmit pressure, and knowing that A is being submitted to the atmospheric pressure, so this liquid will transmit atmospheric pressure to the point A. But here they are telling me only to calculate the pressure exerted by water only, and not the total pressure. So let me make some space here. So the pressure due to this liquid, which is water, let's denote this pressure by PW, W stands for water, is given by the density of the liquid, which is raw water, multiplied by G, multiplied by the depth at which the point B is located, which is given by H1. Now, the density of water is given by 1000, the value of G is given by 10, the value of H1 is given by 0.1. Plugging this on the calculator, then the pressure exerted by water on the point B is given by 1000. Since everything is expressed in the SI, so the unit of P will be in the SI, which is Newton per meter square. And another unit for Newton per meter square is given by Pascal. So the pressure due to water at the point B is given by 1000 Pascal. Notice that in the same part they are telling me deduce the total pressure at B, and by deduce it means that we need to use the previous part. In the previous part you have determined the pressure due to water, knowing that the total pressure at the point B is given by the pressure of water and the pressure of the atmosphere. So let's say B is submitted to the pressure of water and to the atmospheric pressure. So this is important. Usually they give half a mark for this statement. So the total pressure at the point B, which is represented by PB, is equal to PW plus PA. PA is given by P atmosphere. Now 1000 plus the value of the atmospheric pressure, which is given by 103,360. Now plugging this on the calculator, then the value of PB is given by 104,360. Since both this value and this value are expressed in Pascal, so the value of PB will be expressed in Pascal, which is in the SI. So the value of the total pressure at the point B is given by 104,360 Pascal. Let me write here that the pressure at the point B is given by 104,360 Pascal. So notice that if you need to compare, so this value represents the pressure at the point A, and this value represents the pressure at the point B. Comparing both, we notice that PB is greater than PA, which verifies that at the depth, as the depth in a liquid increases, the pressure exerted by the liquid increases. Let me make some space. So actually now we will repeat the same steps, but for documents 1, 2, 3, but for documents 2, 3, and 4. Now, we are in number 4. So this is a bit long. Calculate the pressure exerted by water at point D. So we need to determine the pressure at the point D, but it's due to water, because notice that D is being submitted to two pressures due to the pressure of this layer of water and to the atmospheric pressure, which is at the point C, knowing that according to Pascal's theorem, liquid transmit pressure. So the pressure due to water at the point D is given by the density of water times G times the depth at which we are calculating this pressure, which is given by H2. So the density of water is given by 1000. The value of G is given by 10. and the value of H2 is given by 0.06. Plugging this on the calculator, then the pressure at the point D due to water is given by 600, because everything is expressed in the SI, so the unit of pressure will be in the SI, which is Newton per meter square, and another unit for pressure is denoted by Pascal. Now in the same part they are telling me deduce the total pressure at D, and by deduce it means that we need to use the previous part. So in the previous part we have determined the pressure at the point D due to water, knowing that it's being submitted to two pressures, and this is given by D is submitted to the pressure of water and to the atmospheric pressure. So they usually give half a mark for this statement. So the pressure at the point D is given by PW plus P atmosphere, then 600 plus 103,360. So plugging this on the calculator, then the value of PD is given by 103,960. Since both of these values are expressed in the SI, which is Pascal, so the value of PD will be in Pascal. So the pressure at the point D is given by 103,960 Pascal. And let me write here that the pressure at the point D is given by 103,960 Pascal. So notice that here also the value of PB is greater than the value of PD, although both liquids are water, but simply because the value of H1 is greater than the value of H2, and as the depth in a liquid increases for the same liquid, not for different liquids, the pressure exerted by the liquid increases. And now as for number 5, calculate the pressure exerted by oil at point F. So notice that here F is being submitted to two pressures, the pressure due to oil and to the atmospheric pressure which being applied at the point E, and according to Pascal's theorem, this pressure is being transmitted through the liquid, but here we are interested only in calculating the pressure exerted by oil. So this is given by P oil, or P oil, which is equal to the density of this liquid, which is the density of oil, times G times the depth at which we are calculating this pressure, which is given by H3. So the value of the density of oil is given by 800 from here. The value of G is given by 10. The value of H3 is given by 0.1. Now plugging this on the calculator, then the pressure of oil is given by 800 Newton per meter square, everything in the SI, and this unit is denoted by Pascal. Now moreover, they are telling me to deduce the total pressure at F, knowing that F is being submitted to two pressures. F is submitted to the pressure of oil and to the atmospheric pressure. So they usually give half a mark for this statement. So P, the total pressure at the point F, is given by P oil plus P atmosphere. Now P oil is given by 800 plus P atmosphere 103,360. Plugging this on the calculator, then the total pressure at the point F is given by 104,160 Pascal, simply because both P oil and P atmosphere are expressed in the SI. So PF is given by 104,160 Pascal. Now as for number 6, calculate the pressure exerted by oil at the point M. So knowing that M is being submitted to two pressures, the pressure due to the layer of this liquid, which is oil, and to the atmospheric pressure, which is being applied at the point G, knowing that the liquid, which is oil, transmits pressure, but we are only interested in determining the pressure due to this liquid, which is oil, and we are in number 6. The pressure of oil, which is the pressure due to a liquid, is given by the density of this liquid, which is density of oil, times G, times the depth at which we are calculating this pressure, which is given by H4. So the density of oil is 800 multiplied by G, which is 10, multiplied by H4. H4 is given by 0.04. So plugging this on the calculator, then the value of P oil is given by 320. Since all of these are expressed in the SI, so the value of P oil will be in the SI, which is Newton per meter square, and also which is denoted by Pascal. Now in the same part, deduce the total pressure at M, knowing that M. So notice that here below the point M we have water, but always whenever we are interested in pressure, we always look upward. We don't care what is below this point. Now M is submitted to the pressure of oil and to the atmospheric pressure. So P at the point M is equal to P oil plus P atmosphere. So the pressure of P oil is given by 320 and the atmospheric pressure is given by 103,360. Plugging this on the calculator, then the pressure at the point M is given by 103,680 Pascal. So the pressure at the point M is given by 103,680 Pascal. This is also Pascal. Now in number 7, the pressure at G is transmitted to M and to N according to a certain theorem stated. So they are telling us that the atmospheric pressure, which is at the point G, is being transmitted to the points M and N, and this is according to a certain theorem. We need to state this theorem, and this is known for sure Pascal's theorem. But it's not enough to mention the name of this theorem, we need to state it. So it's given by liquids transmit wholly and in all directions the variations of pressure to which they are submitted. And now as for number 8, calculate the pressure exerted by water at the point N. So notice that here in this case the point N is being submitted to two pressures, to pressure due to water and to the pressure at the point M. We are interested in determining the pressure at the point N. So the pressure, at the point N due to water. So let's say Pw is equal to the density of water times G times the depth, which is H5 in this case, because the layer of water has a depth only H5 and not H4 plus A5, because if you consider H4 and H5, we need to consider two liquids and they are given by oil and water. So times H5, the density of water is given by 1000, the value of G is given by 10, and the value of H5 is given by 0.03. Plugging this on the calculator, then the pressure due to water at this point is given by 300. Since everything is expressed in the SI, then the unit of PW will be in the SI, which is Newton per meter square, and also denoted by Pascal. Now in the same part they are telling me deduce the total pressure at N. So notice that here N is being submitted to two pressures, the pressure due to water and to the total pressure at the point M. So if we need to say, like we were doing previously, that N is being submitted to the pressure of water and to the atmospheric pressure, we also need to consider the pressure due to this layer of liquid, which is oil. But we can simply say that the pressure at the point N is due to the pressure of this layer of liquid, which is water, and to the total pressure at the point M, which is being also transmitted to the point N according to Pascal's theorem. So let's say that N is submitted to the pressure of water and to the pressure at the point M. So in this case, the pressure at the point N is equal to the pressure due to water plus Pm. The pressure due to water is given by 300, and Pm, which is the total pressure that we have calculated in number 6, is given by 103,680. Now plugging this on the calculator, then the total pressure at the point N is given by 103,980. Since both of these are expressed in Pascal, so the value of Pn will be in Pascal. So this is the total pressure at the point N, which is given by 103,980 Pascal. Now we have reached number 9. Calculate delta P, the variations of the pressure between the 2 points A and B. So delta P between the 2 points B, A and B. So here we can either say that PA minus PB or PB minus PA, but we always start with the point which is located at a horizontal level, which is lower. So we will choose this. So PB minus PA. The value of PB that we have calculated is given by 104,360, which is this, minus PA, which is the atmospheric pressure, 103,360. Now plugging this on the calculator, then delta P is given by 1000. Since both of these are expressed in Pascal, so the value of delta P, which is the variation of pressure or the difference in pressure between the points B and A, is given by 1000 Pascal. So another way to calculate the difference in pressures between the points B and A is from the second definition, which is given by that delta P is equal to the density of the liquid times G times H, in which H represents the difference of levels between the points B and A, which is given by H1. And here the density of the liquid is given by water, so let me write raw water. Now if you replace the value of raw water by 1000, the value of G by 10, the value of H1 by 0.1, if you try this, you will get the same result. But since we have already calculated these pressures, let's use the definition of delta P, which is the difference between the pressures at 2 points, in order to calculate its value. Now as for number 10, we need to calculate delta P, the variation of pressure between the points C and D. So delta P, now we have two choices. Either we write PC minus PD or PD minus PC, since D is located at a horizontal level lower than that of C. So we will start with it, which is PD minus PC. The value of PD, which is given by 103,960, minus the pressure at the point C, which is the atmospheric pressure. Now plugging this on the calculator, then delta P is given by 600 Pascal. Now as for number 11, we are interested in determining delta P, which is the variation of pressures between the points E and F. So because F is located at a horizontal level lower than that of E, so we'll start with it. So then PF minus PE which is equal to the pressure at the point F is given by 104,160 minus the atmospheric pressure, which is the pressure at the point E. Plugging this on the calculator, then the pressure is given by the difference in pressure is given by 800 Pascal. As for number 12, delta P, which is the difference in pressures between the points G and M. Notice that because M is located at a horizontal level lower than that of G, so we will start with it. PM minus PG. The value of PM is given by 103,680 minus the value at the point G, which is the atmospheric pressure. Plugging this on the calculator, so it's given by 320 Pascal. Now finally in number 13, delta P, the variation of pressures between the points M and N. So because N is located at a horizontal level lower than that of M, so we'll start with it. So it's Pn minus Pm. The pressure at the point N is given by 103,980 minus 103,680. Plugging this on the calculator, then the variation of pressures between the points N and M is given by 300 Pascal. And by this we have finished solving this exercise. So that's it for me in this video, guys. In the next part 3, we will complete solving exercises on this chapter.